So okay, hello everyone. So I place my camera. It quite be seen risky, so you can see everything. Okay, so my hands are free now. First I was recording using one hand and shifting another. So I place the camera, but I don't currently have tripod, so I was not quite sure it stay on the place. Okay, let's start. So my name is Kedar Bhame. So I was telling you the Intel x86 processor architecture, how it runs our program and how the output will return. There are 9 steps in that. The first step I was telling the which our program is currently stored on hard disk. Suppose our program name is hello.c, which gets to the passes through the compiler. Compile will compile and generate the output. So now what the compilers means in our case, I tell you first. The compilers include the preprocessor, the compiler, and the assembler. Okay, I already tell what these three do. And our assembler will generate ASM file, means the current state our compiler will generate ASM file, and the hello.asm file compiler will generate object file. No, assembler will generate object file. Sorry for misconception. Object assembler will generate object file, means the compiler will generate object file in current state. The hello.obj is currently, suppose we have you can see in the diagram. I can paste plot it here. The hello.obj include text, data, and symbol table section. Text include the binary instruction of the current program, means our hello.c program, and the data section is used to memory. Data section have memory for the what we call variables, which we use global variable or the static constant variable, I guess static or constant variable. For that the memory is required, so that things is in the data section. And symbol table use the everything about symbols, so means the program use normal variable, I guess, that stored in the symbol table. Now this everything means the hello.obj file passed to the linker link with the other hello.obj file and expand it. I was tell you the how it will do. Okay, so linker, I told you expand the file, means they our get hello.obj, and there is other files our hello.obj can't run. It should be converted into hello.exe, but it won't convert directly because we need it not, because it was not complete a file. the we want to make our hello.obj into hello.exe, which required other.obj file. There are other file we generally now for particular scenario calling it other file, other.obj file. The other I will get some back, I guess. The other.obj file, which same content, it has the text, the data, and symbol table, but on the text it have primary header ph, which includes the our programming, what we call machine dependency. There is code for machine dependent. There is code which is written there, and there other things on that, I guess. The now it file okay, now it file okay, ignore it. Now the file will go to the RAM using loader. There is second step. We first file our pass hello.c to compiler, then the output of compiler is hello.obj, then they pass to the linker. First step is done, then second step is go to the linker will link hello.obj plus other.obj and give the hello.exe, which is fully executed file, which has ph, means primary header, and text, data, and symbol table, 4 sections. So okay, this file go to the RAM. So we use loader is come from OS. The third we use is loader. On the RAM there is operating system already present. Without operating system we can't go directly without operating system. The operating system is already present there. So now what are we doing? We go in RAM. There is our third step. Okay, a loader will do that. Or loader has loader comes under operating system. The loader will load. So now what we sections we have, I tell. The first one is text section, which stores the binary instructions of our program. The another one is data section, which stores same the what we call the data section. We store the static variable or the constant variable, I tell already. Yeah. And another is stack. So now we remove, you can see we remove ph, and what the second one I can't remembering now. Symbol table, yeah, ph and symbol table. When our program come from hard disk to our RAM, before it was till the third step, it was second step, it was on hard disk. The third step is put the from hard disk to the RAM, it to hello.exe, which is on hard disk. Now we put on the RAM. So we remove ph and the symbol table from that and add another section stack. Add another section stack there. The stack currently holds the our program is okay. I forgot to tell you one thing. Our till that before third step, our we have hello.exe, which is a program. But when it come to RAM, it was not a program, it was a process. So we can call it hello.process, which include text, data and stack. Okay, we remove ph and symbol table because we don't need that in the execution phase. We use the what we call stack. Okay, there are three sections. Already operating system was there. Okay, so now we need to pass that on CPU, but CPU can't get that big memory at a time. What CPU said, you can give me chunk of memory. So we can there is execution control unit. They have segment, I guess, yes, sections in the RAM and segment in the CPU. So in this first section is CS, mean code segment, which we transfer our text section to the code segment. The second one is data SDS, mean data segment. We transfer our data from RAM to the data segment on our CPU, which is all these are registers. And the third one is SS stack segment. We transfer our RAM stack. We told you in the our hello.process there is data, text, data and stack section. So stack section will transfer to the stack section segment to the CPU, means electrical what we called it. There are registers in the CPU, we transfer there. And there is other segments, RCU, register control unit, I forget the name, which comes under CS. We discuss CS. Then after that there is code segment CS, then the data segment DS and the stack segment SS. After that EF, GF, extra segment, F, S and GS, EFG, and we got S. EF is the extra segment and EF, S and GS is also same like extra segment. Whenever additional memory is required, we can plot there. So after that, so this is fourth step, right? We load our program from the RAM, from hard disk to RAM. It is our third step. And now we are moving from the RAM to the CPU. It is our fourth step. I mean, not the CPU, the RCU, register control unit in the CPU. So now what are we doing? This program not the program. After the RCU, register control unit, the program will go towards what we called the instruction queue. All we call it queue. There are converted into instruction one by one. There are many instructions for the CPU, but we can only pass one at a time. So there is queue, and after queue there is IP. There is instruction pointer. This suppose this like a bouncer which pass only one instruction at a time. The IP is responsible to send the CPU one instruction at a time. So this is our 6 step. Okay, no, this is our 5 step to transfer our register control unit RCU the data from the queue. Okay, RCU includes CS, DS, SS, and extra segments, and after RCU we pass to the queue, instruction queue. This is our 5th step, and after 5th step we have, before 5th step we have IP, instruction pointer. We will send one by one instruction to the CPU. So we will move towards 6th step, which includes the 3 main subsection: ALU, arithmetical logical unit. Here perform all the tasks related to the arithmetical calculation. And the second one is control unit. Here perform all types of tasks, arithmetical, like GPU. All tasks is performed on CPU control unit. And third one is flag. Flag is used for to determine what these both are doing currently. Just like the operation theater, in the doctor there is a particular light. So suppose we have red, yellow, so even our operation theater we can use traffic light. So how they are telling us stop, you can don't go ahead. If the red is stop, you can stop. The yellow is for signal to slow down your vehicle, and green for is go. Same like flags indicates to the other components, like currently CPU is like processing or whatever CPU is doing, the indicates using flag, CPU or ALU, I guess. I'm not quite sure, but yeah, they both there is a flag section which indicate what the execution is currently happening in CPU. Okay, after we are now 6th step. After 6 we can go in the 7th step. Okay, the 7th step is it passes to the general purpose register, which are like I guess there is a high or low, 2 types of register. First is A, H and AL, means the arithmetical register which perform arithmetical logical arithmetical processing. I guess AL, we can suppose we have AL. Its camera is moving, wait a second. Yeah, so instead of calling, I first tell name what our we have general purpose register. AH, AL, then BH, BL, base register, CH, CL, which have count registers, and DH, DL mean data registers. Okay, so there is 8 types total, but we can count in 4. Instead of H and L, we can combine 2 and call as AX, means AX include AH and AL. Same for BX. BX is also include B, H or BL. Okay, so we count as AX, BX, CX, DX. So AX is responsible for arithmetical unit, BX is responsible for base registers. I don't know what it do currently. Then CS is for counting, so count register, and DS is for data. Everything is data. We are here for data. We are performing CPU calculation data, I guess. Then before after that there is pointer registers. First come is stack pointer SP, and the second one is BP. After this 8 AX, AL, BX, BL. After 4 there below there is SP, means stack pointer, which is point to the data segment DS in the RCU. I not quite sure, but it point there. And the SP, and after SP there is BP, base pointer, which point to the extra segment in the RCU. We discussed ES specially, or FS or GS also coming extra segment. So that point there mean the BP, base pointer point there. BP is a pointer register. I told you SP and BP static pointer and base pointer. So after that there is index pointer register, which include I was quite not sure what is include base pointer register. It includes BP. SI means start index. DI, I guess DI was there. So ignore that. There are two registers there. I currently not remembering that. Oh yeah, there is SI for starting index, I guess. Ignore that. We go to the next step. What step we are currently of? 5, 6, 7. We are currently of 7 step. We are here. Now we go to the 8th step using IDB integrated data bus. We travel to data bus and using FSB. The 9th step, which is part of IDB. FSB is the part of IDB. We can go towards OS. This is our 9th step. Okay, so our this whatever our operation we perform there and pass the output to our using towards the operating system. This is 9th step from FSB to the OS. This is 9th, and the from the registers to the general purpose registers to the IDB. This is 8th step. So we pass 8 and 9th there to the operating system. The operating system is responsible for the showing output to the user using console. So now I want to tell you, OS operating system has 5 tasks. First is file managing. Everything is can be storable. It is stored in the file. So everything is storable. It is stored in the file. Okay, and every file is stored in the hard disk. Hard disk means the hard disk SSD or CD. Okay, so first task of the operating system is to file management. Okay, so OS will manage all the files in your hard drive. Then the second task is to memory management. In case what memory means is the RAM. So RAM allocation, deallocation. The new program come give the memory, or they are taking too much memory, get from that. The restriction, all the RAM management is operating system task. We call it memory management. The second and the third one is also management. What may it manage? CPU scheduling is the fourth task, I guess. File management, memory management, and instruction management. Not file management, memory management, and the third one, I guess, not recalling. We will discuss about CPU scheduling. We discussed this is fourth one we are discussing. The third one I was not currently remember. The fourth one is CPU scheduling. So there are many instructions for CPU. The CPU scheduler will discuss which instruction go first and which is like currently don't go there, the scenario. Okay, the CPU instruction, CPU scheduling. The CPU scheduler will discuss which instruction go to the CPU or which don't go, or go by delay. Okay, and there is an emergency instruction. Then CPU will pass to what we call CPU get instruction for CPU registers, I guess. Scheduler, CPU register. Okay, and another is hardware abstraction. Oh, I remember the third one is process management. Another process is from the First we discuss file management and memory management. File management on hard disk, memory management on the RAM. The third one is process management. I was ignorant. There are many processes for the computer or the CPU. The CPU process management is discuss which process go first and which go. Suppose we are discussing we create hello.file and other many hello.1, hello.2 we are executing at the same time. There are come in the RAM. They are all processes. The process management is process management is discuss what in the discuss we decide which go first, which will go second. Okay, and after that I tell you CPU scheduler. This will be fourth. CPU scheduler will there are after processes they process divided into instruction. CPU scheduler will discuss which instruction go first, and CPU only accept one instruction at a time, right? So CPU instructor CPU scheduler will decide which instruction go for CPU first and second, and they structure their instructions. Okay, and the fifth one is hardware abstractions, mean the internal working of our computer is not visible to user. Just we use our graphical pointer or whatever. There is no complexity. Suppose you press the keyboard, like pressing keyboard, and keyboard there is complexity in the keyboard, like there is x-axis, y-axis. If we we physically click, the computer will know this binary code, hexadecimal code for this key, and this travels to monitor and whatever process. So there is keyboard is doing hardware abstraction, like every time we don't remember 0 1x for hexadecimal number for this alphabet. The hardware, all everything is hardware. There is complicated hardware extracted from user don't see the complexity. They just can use generally everything without that complexity using GUI and other format. So that is called it hardware abstraction. This is the most essential thing in the hardware in the computer on the operating system. If this was not present, I guess so every computer will not grow eventually that big. So there is too much complexity inside computer. Okay, so now what are we discuss? We are summarizing here. 22 minutes happen of this video. So now we are summarizing this. We discuss about x86 architecture. Okay, the how our hello.c was converted to compiler, which compile that hello.exe hello.c file to the hello.obj file. The first step is come hello.obj. The second is linker will get do hello dot our obj file and other dot obj file with compile and make hello.exe file. Linker will make that. We are currently on our hard drive for currently these two steps. Now we shifted to RAM. How we shifted to RAM? Our loader will help you. Loader is operating system part. Operating system was already present on our RAM before we reach. So loader over there. Loader help us to load our program on the RAM. Our program loaded on RAM. We remove its ph and table symbol table, and I add stack segment here. After that our program from RAM go to the CPU. Inside CPU there is section called register control unit. Our program was go there. Different section of our RAM goes to different sections. CS data section, code section, and other sections. Stack section, CS, DS, SS. Code, data, stack sections. Extra segments is also there. Now after fourth stage we are on CPU on the special unit ICU. After that we go to the instruction queue, which is our sixth step. So I shift here sixth step. So sixth step we go to the instruction queue. There are many instructions for CPU. We can pass only one instruction at a time. After we pass one instruction, there is CPU means CU control units, ALU arithmetical logical unit, and the third one is flag, which is three sub part of this CPU. The CU can perform any instruction. The ALU can perform arithmetical instruction, and the flags which determine which these both are ALU and CU. What are they currently performing? Their currently information about they what the ALU and CU currently performing, the information about that, the flag which tells to everyone, I guess. The flags is responsibility to tell what the CU and AU was performing. After that, we are here 4, 5, 6. I guess 6 step was here, and then the 7th step we go to the general purpose registers, to the CPU. The CPU inside there is, we generally summarize in the 4 AX, means arithmetical or accumulator. There is special word accumulator registers, AX, and there BX for base registers, then CX for count register, and DS for data register. AX, BX, CX, DX. Okay, the 4 is general purpose register. So AX is include AH and BAH and AL, high and low, and same BH and BL. So they are 4 register. There after that there is which register, after that they have pointer register, static pointer, one base pointer. Static pointer points to the data segment in the RS register controller is RCU, and the BP means base pointer is point to the extra segment in the RCU. Yes. Okay, so till now we are here 1, 2, 3, 4, 5, 6, 7. We are currently on the 6th step. 8th step, no, we include SI, index pointer, static index, starting index pointer, and DI, I guess, index pointer, also 2 register we discuss. And after that we are currently 7th step. Now we go to the 8th step, which is here. The 8th step is to what we do in the 8th step, we transfer our calculation to the IDB, integrated data bus. Inside IDB we transferred 8th step our complete. And the 9th step is inside IDB there is section FSV, which transfer our output to the operating system. This is our 9th step. We transfer our output using FSB of the IDB, integrated data bus. There is section FSB, we transfer using that to the operating system. The operating system is now responsible for our showing the output to the user. So okay, we discussed that everything in our what we called Intel x86 architecture. So we will currently stop here. Okay, so and we will discuss 5 tasks of operating system. The first one is the file management, the second one is the memory management, the RAM management, third one is process management, only one process get at a time, I guess. Yeah, and the third one is CPU scheduling, only one CPU instruction can the process, there are many processes and can execute every time, but the CPU scheduling is the, we can for the CPU there are many instruction, but one perform at a time. So CPU instructor will decide which operation perform first, second, or the sequence of that. And the first one is file abstraction. I tell you, this was the main thing in the operating system. This will hide all the complexity of the computer from the user. Like a 7-year-old can use the computer, but they don't know how your file will get transferred, and how the CPU run, how there is segment, how register, how it pass to operating system, what is OS. So they don't need to do everything. Will get them. There is remove the complexity. The task is for hardware abstraction. This is the 5 tasks of operating system: file management, memory management, process management, CPU scheduling, and the hardware abstraction. Okay, so x86 architecture, Intel x86 architecture we will cover, and the operating system task, 5 major tasks we covered in that video. So thank you. So 28 minutes it will go. So that's a big video, I guess. Thank you. And also one thing, this video is recording fee for me. I was now watching this video and understand the knowledge I have, or the way I talk. I want to improve that. That's the main purpose of this video. If you don't watch this video, I also don't care. If it doesn't watch my video, I post to YouTube or other platform or my phone. If anybody don't watch this video, I don't care about anyone. This video I created for me to understand how I was talk and improve myself. Okay, thank you.